Welcome back. So in this lecture, we are going to study what is known as the Gibbs phase rule. We will see that this Gibbs phase rule, it follows from the condition of the joint equilibrium of a system. Right? Now we have already seen the stability criteria for entropy and internal energy. Here, let us consider two systems with entropy U1, V1 and N1 and S2 as U2, V2 and N2, and let us bring these two systems. So two systems. Let us be but first we note that U1 plus U2 must be your total energy, V1 plus V2 must be your volume, N1 plus N2 is going to be your total particle number. U, V, N are being held fixed. So bring them together so that they come into a joint equilibrium. Alternatively, you can imagine that I have a system, let's say a gas, which has U, V and N is described by this fundamental relation. I can partition them into two subsystems such that they have entropies S1 and S2 as we have written now. So once they come to a joint equilibrium, we will write down the total entropy as UVN, which is going to be S1, U1, V1, N1 plus S2, U2, V2 and N2. Now any change in this entropy near this joint equilibrium, let's calculate that, is going to be del S1 del U1 du1 plus del S2 del U2 du2 plus del S1 del V1 dV1 plus del S2 del V2 dV2, and similarly you have for the particle number, which is going to be del S1 del N1 dN1 plus del S2 del N2 d of N2, and then you have higher order terms which you ignore because you are, let's say, you are very infinitesimally close to the equilibrium point, the joint equilibrium point. Now clearly at the joint equilibrium point the delta S is 0. That's a stability criteria if it is a stable equilibrium point. So this means the left hand side is 0. Now let's look at this term. From here, if I see, since U is fixed, it means that du1 plus du2 is going to be 0. Now dv1 plus dv2 is going to be 0 and dn1 plus dn2 is also going to be 0, which means you can imagine that if I move this partition infinitesimally to the left hand side, some of this, so this was n2, this was n2, and this was one n1, this was one n2, this one was v1, this one was v2, and you can see that a part of this volume goes, if you just move the partition a little to the left. This is an imaginary partition, by the way. You're not really putting a partition, but you're imagining that you have broken the system into two subsystems using an imaginary partition, and this partition, if you move to the left a little bit or to the right, you see v1 and v2 are going to change. So any change in dv1 will be compensated by a change in dv2. That is exactly what this relation tells you. Any change in particle number dn1 in this is going to be compensated by particle number dn2, so that dn1 is going to be minus of dn2. If you move, for example, I have moved it to the left, which means n2 has increased and there is a change in n2, which we will denote as dn2. Since it's the same system with the number of particles fixed, therefore n1 number of particles n1 should decrease. So we have these three relations. Let's substitute over here. Then you see that this term is del s del u1 minus del s2 del u2 times du1 plus del s1 del v1 minus del s2 del v2 dv1 plus del s1 del n1 minus del s2 del n2 times d of n1. Since the left hand side is identically 0 and this is valid for any arbitrary variation in u1, v1 and n1, it follows that del s1 del u1 is going to be del s2 del u2. I have suppressed the factors, variables which are held constant. You can easily figure them out. This means del s1 del v1 is going to be del s2 del v2, and this essentially means del s1 del n1 is going to be del s2 del n2, right? Provided the state you are looking at, final state, is an equilibrium state. If it's an unstable equilibrium, the system might spontaneously go to a new equilibrium state, and in that case delta S is not going to be 0 and we cannot argue in this manner. But these thermodynamic relations all of you know. This means 1 over T1 is going to be 1 over T2 is going to be 1 over T, so that I have T1 T2 is equal to T in the joint equilibrium state. This means P1 by T1 is going to be P2 by T2, and since T1 is equal to T2, I have P1 is equal to P2. And similarly, this would mean that mu1 over T1 is going to be mu2 over T2. Once again, since T1 is equal to T2, this is going to be mu1 over mu2. Therefore, you see, a joint equilibrium. What does a joint equilibrium means? A joint equilibrium essentially has these three conditions. This is for a hydrostatic system you are looking at. This condition is what is called a thermal equilibrium. This condition is what is called a mechanical equilibrium. And this is what is called a chemical equilibrium. So in general, for any arbitrary thermodynamic system, an equilibrium state essentially means that you have a thermal equilibrium, temperature is uniform. You have a mechanical equilibrium, which means the balance of the external forces that describes the thermodynamic state of the system, and the chemical equilibrium, again, that essentially means that the chemical potentials must be same. Now suppose I have a system. So here, whatever we have considered a single component, one type. For example, our system was made up of one type of gas particles. But now let's complicate things a little bit more. We take a system which has n components. But that's not the whole story. Now each of these components have R phases. So essentially you're looking at an equilibrium, a joint equilibrium between these n components, and each of these components can exist in R phases. For example, I can expect that there is a solid 1, solid 2. So if one of the two components, one of them can be in a phase solid 1 and the other phase solid 2, and the other component can be in a liquid phase. So this is a joint equilibrium that we are talking about. Now we have clearly seen what does the joint equilibrium means. So let's write down. So the temperatures must be equal. Tn must be equal to the temperature. We will take the case of a hydrostatic system, and therefore we will write down the pressure must be all equal for this. These are the trivial things. There is a balance of mechanical force, which is the mechanical equilibrium. This is the mechanical equilibrium, and this is the thermal equilibrium. Now, if you recall, your first law is TdS is du plus pi dvi minus sum over I sum over mu y r d ni r. So please understand that you have to be very careful with this. But these two are done. The thermal equilibrium is done, the mechanical equilibrium is done. The point comes in for the chemical equilibrium. The chemical equilibrium essentially tells me that I have mu1 is equal to mu2 for a single component system, but now one has to be careful that mu1 of 1, phase 1, the superscript denotes the phase, must be equal to mu1 of 2 is equal to mu1 of r. That's what that chemical equilibrium would mean. One should then look at, write down for mu2 is going to be mu22 is going to be mu2 of r. So this is a chemical equilibrium between the phases, and one has mu n of 1 is going to be mu n of 2 all the way up to mu n of r. So now for this joint equilibrium, I want to now figure out how many possible coordinates, thermodynamic coordinates, I can vary independently. So which means that this joint system, how many thermodynamic coordinates describe that, and that is essentially the degrees of freedom of the system. Of course, two of them are known, which is T and P, the temperature and the pressure, right? Now note that I have n components, which means the number of particles in component 1 plus number of particles of component 2, so on and so forth, all the way up to nn is going to be capital N, total number of particles, and that is fixed. So which means C1 plus C2 and all the way up to Cn is going to be 1. Now this condition itself tells you, since total particle number is fixed, that if I know C1, C2 and all the way up to Cn minus 1, I actually know Cn, which is 1 minus C1 minus C2 going up to Cn minus 1. Therefore, how many coordinates you have? You have C1, 1, C2, 1, C3, 1, going up to Cn minus 1 of 1 for phases 1. Then you have C1 of 2, C2 of 2 for phase 2, going all the way up to Cn minus 1 of 2, and you continue down to come to the phase, rth phase, which is C1 of r, C2 of r, going up to Cn minus 1 of r. So that you see here that there are r rows and n minus 1 columns, and therefore you have r times n minus 1 coordinates over here, so that the total number of coordinates is r times n minus 1 plus 2. But not all of them can be independently varied, because I have this restriction that restricts the chemical potential. This is a equilibrium, this is an equilibrium condition for the this is a chemical equilibrium between the different components and their phases. And here you clearly see that I have n equations and r minus 1. So your constraints are n times r minus 1, and if you denote f as the number of degrees of freedom which you can independently vary, so let this be the number of degrees of freedom that can be independently varied. F is the total number of degree of freedom which you have, which is 2 plus n times r minus 1 minus n times, no, this has to be, sorry, this is 2 plus r times n minus 1 minus n minus r minus 1. And if you do that, then this is 2 plus nr minus r minus nr plus n, which is 2 plus n minus r. So you come up with this relation, which is 2 plus n minus r. And this is what is called a Gibbs phase rule. Say I have n equal to 1, a single component, and r is equal to 1. It can exist in only one phase, which means your degree of freedom f is going to be 2, and the variables you can vary are t and p, which is typically for a liquid. If n is equal to 1 and r is equal to 2, then you see the number of degrees of freedom you have is 1. So this means that, for example, if you have a liquid vapor coexistence, this is the case, which is the coexistence curve. P as a function of t, let's say P naught as a function of t. This gives you the coexistence curve, because a single component, a liquid, let's say water, which can now coexist between water and water vapor, and then you have this coexistence curve that essentially you can vary only one of them to move along the curve. If you have n equal to 1 and r is equal to 3, a single component which can exist in 3 phases, for example solid, liquid and gas, then you see f is equal to 0. You have no freedom in the phase diagram, in the PT phase, in the thermodynamic phase diagram, and essentially this represents a point, which is the triple point for a hydrostatic system, right? So with this we conclude this lecture.